Good afternoon, everyone, and thank you for joining me as I provide an overview of four of the work scopes provided or proposed under our Material Recovery and Wastewater Development Program. So I'd like to start by giving an overview of our Material Recovery and Wastewater Development Program. This program focuses on developing innovative methods of recovering valuable elements from used nuclear fuel and also managing the resulting waste that are generated from it. So basically think of all the ways in which you can close the nuclear fuel cycle. So that includes reprocessing, both aqueous and pyroprocessing, off-gas capture, and waste form development. And so our program has developed decades of unique experience in the areas I just mentioned. And so this year for the NEUP call, we have identified 5 topics that we think will help us accomplish our mission in that program. And I'll be talking about the first 4. Kimberly Gray is going to talk about the 5th one later on today. So the first topic is on innovative separations chemistry for high value used nuclear fuel. So many of you know that the nuclear industry right now is in a sort of exciting time, in my opinion. There are a lot of new and advanced reactor technologies like molten salt reactors, microreactors, sodium fast reactors that intend to use high assay, low enriched uranium fuels or HALEU fuels that are significantly more enriched than conventional light water reactor fuels. So we're talking about, up to 19.75% enriched as opposed to the 3 to 5% enriched that you normally see for light water reactor fuels. And so, as I mentioned in my previous slide, one of the main thrusts for our program is developing technologies to separate uranium and plutonium and other elements from light water reactor fuels, specifically on making economic methods of doing that. And so we think that in this case, if we recycle used HALEU fuel, that could prove a lot more economical for recycling than the traditional light water reactor fuels, because they're still going to contain a significant quantity of that valuable high assay low enriched uranium. And so most of the thrust in our program, or the focus of our program in the past, has been on using solvent extraction, which is the most heavily researched method of separating uranium, plutonium, and minor actinides. We've also looked at pyroprocessing, but there are other separations methods that have been less studied, including selective oxidation, precipitation, and dry processes such as halogenation. And so for this particular topic, we're looking for applications that are proposing innovative or simplified methods of recovering this uranium, high assay low enriched uranium, as well as other valuable actinides from fuels that can include HALEU, that can contain HALEU. So we're talking about metallic fuels, TRISO fuels, molten salt fuels, right? And so this program, or this call, is funded up to 2 years and up to $400,000. And so one thing I just want to take a moment to say is that I really like this topic because it's focused on innovation. We are really looking to you, the universities, to propose innovative methods for doing this type of recovery. I think the universities are a hotbed, the best, ideal location for doing innovative research. And I think that this type of innovative research can help inspire the next generation of nuclear researchers. So the second topic that we have is on nuclear fuel cycle separations chemistry. So this is a broader topic than the first topic. And so, as you all know, basically every stage of the nuclear fuel cycle, from mining and milling all the way out to reprocessing and recycling, they all involve some form of chemical separations that are used. You probably also know that these separations are usually focused on uranium and plutonium recovery for recycling and or for other uses in the fuel cycle. But we recognize that there are other valuable isotopes that could be recovered, for example, rare earths, right? So we think that by developing advanced separations processes and technologies for both actinides and other valuable elements can further enhance the economics of used fuel recycle. And so for this call, we are looking for applications that are proposing innovative research on fundamental separations chemistry. So some of the topics include looking at coordination chemistry, radiolysis and solvent extraction systems, and even computational modeling. And so this project is funded up to 2 years and at up to $400,000. So now we'll switch gears for the next two topics and talk about molten salt chemistry. So these last two topics focus on molten salt chemistry research. FC-1.3, the title is Understanding, Predicting, and Optimizing the Physical Properties, Structures, and Dynamics of Molten Salts. I know that's a mouthful, but that is the title. And for this one, you all know that molten salts are used in a lot of different areas, primarily in pyroprocessing, obviously for molten salt reactors, but even in the solar industry for potential solar towers. And so this is a burgeoning area that has a lot of interest, the use of molten salts is. And as such, there are a lot of data gaps and things we don't quite understand about molten salt behavior. And so in order to be able to address these things, we need to have experimental data, but also thermodynamic models that can be used to predict these salt characteristics like melting point, heat capacities, and other properties as a function of temperature and composition. And so for this call, we're looking for proposals that'll help us understand the physical properties and thermochemical behavior of molten salt, specifically by using computational methods like first principles molecular dynamic simulations, as well as computational electronic structure methods that will enable us to basically extend the limited data that we have on molten salt to be able to model a broader molten salt environment, if you will. And so we're looking for innovative approaches to, again, apply molecular dynamic simulations to predict thermophysical and transport properties, being able to enable prediction of phase diagrams, and importantly, and I think ultimately, we want to be able to use these models to help guide future experimental efforts to optimize the salt properties for molten salts for these applications that I mentioned earlier. And so this is another project that's funded at up to 2 years at $400,000. And so the last topic in our area that I'll talk about today is more on the experimental side. So FC-1.3, I want to make it clear that that one's looking more at computational methods, but this one is focused more, if you will, on the experimental methods. And so in this case, we think that in order for us to, we need to have a good understanding of the speciation of molten salts, as well as the local and intermediate structures of these salts at operationally relevant temperatures in order to be able to understand how they influence the physical and chemical properties of these salts. And so under this proposal, we're looking for those that propose innovative tools and instrumentation that can allow us to get data at the atomic and molecular scale. And so the ultimate objective here is to be able to develop or determine and understand, if you will, the structure and bonding, and also identify chemical species in salt solutions, and also to develop real-time analytical models for enabling microscopic and macroscopic property measurements. And so I have a list here of different topics that this includes. It's not exhaustive, but just briefly, it includes being able to use scattering and spectroscopic methods to determine local salt structure and speciation. Also to develop spectroscopic measurements for in situ monitoring and predictive monitoring, so that's very relevant for molten salt reactors, for example, to be able to understand corrosion and other behaviors. And then lastly, to develop a molten salt optical basicity scale to determine corrosion and solubility of actinides. And so this project, unlike the other three, is actually funded for 3 years, up to $600,000. And so lastly, I just want to talk about a complementary work scope that you'll probably see in the final document when it's released. This is in the nuclear energy advanced modeling and simulation area on corrosion modeling for molten salt facing structural components. Now, this is another topic that involves computational modeling for molten salt. And in this case, it's looking at modeling the interactions of molten salts with structural materials that are present in reactors and molten salt reactors under real-time conditions. And so I just want to make it clear, like, even though this is another computational modeling topic for molten salt, it's not overlapping our FC-1.3 scope. In fact, they're actually complementary. So as I hope I've adequately explained earlier, the FC-1.3 scope that we have is focused on atomic and molecular scale modeling of molten salt behavior, like fundamental molten salt chemistry behavior, whereas this scope is focused on mesoscale, even bulk scale modeling of salt interactions with structural materials. So I've been in contact with, and communications, if you will, with the NEAMS teams about this work scope and about our work scope to make sure that, moving forward, we are coordinating our work scopes accordingly. So if you're interested in more mesoscale, bulk scale modeling, I recommend you contact Dave Henderson at the email address listed here below. And so with that, I will stop and take a moment to answer any questions you have, but alternatively, you can contact me at the email address listed here. All right, thank you.
Okay, Christina, it looks like we do have a few questions. First one, is the recycling of HALEU only focused on recovery of uranium and maybe plutonium, or could it be expanded to look at the other valuable elements and isotopes?
Yeah, so the main focus really is on uranium and plutonium. I think it's a lot more valuable than some of the minor actinides, especially for HALEU fuels because of that higher enriched uranium. But I can understand the need to recover other actinides for waste management purposes, if you will. But I will say that this focus is really on that highly valuable uranium and even plutonium for recycle.
Okay, is the recycling of HALEU in light water reactor fuel a part of the scope?
Yes, so it's any kind of fuel that contains HALEU. So that, that's going to include, traditional oxide fuels that may have HALEU, metallic fuels, triso fuels, molten salt fuels. So yeah, that's also part of it, as long as it's HALEU fuel. Yep.
What form is expected for the spent fuel to be separated? Dissolved in nitric acid or something else?
Oh, that's a good question. So we're not restricting that what the form of the spent fuel can be in, right? This is where you can be very innovative, right? So that spent fuel is normally dissolved in nitric acid, on the front end for recycling or reprocessing, and then subsequent recycling. But if you can propose a process that doesn't involve dissolution in nitric acid, that's great. Or if you have one that's in, it requires dissolution in hydrochloric acid to achieve the separation that you're talking about, that's fine. But it's really just, we're leaving it up to you to be as innovative as possible with respect to recovering the uranium and plutonium.
Okay, this is still an FC-1.1. What level of purity of the recovered uranium from HALEU is required, such as high purity for use in a light water reactor or lower purity for use in an advanced reactor?
So again, we're not restricting you on that because, as you pointed out, the purity requirements are going to be different, right? And the advanced reactor designs that are out there right now include both thermal and fast reactors. And so, some of them, like the sodium fast reactors, they're going to have a different purity requirement than, say, a molten salt thermal reactor. So we're not going to restrict you in that area because any of them, there's a range of purities that will be required. So I'd recommend, tailoring your proposal to achieve the purity that you think is relevant for these technologies.
Okay, is the spent fuel in the original form, such as metal, triso, etc.?
Yeah, I think this sounds similar to a previous question, but the fuels can be in any form. So there can be triso fuels, metallic fuels, etc. And so we're not limiting you to, fuel that's already been dissolved in nitric acid. If you, again, as I said before, if it can be done without the solution in nitric acid, like via a dry process, for example, that's even better. Just something that's innovative. But do recognize that the HALEU fuels that we're talking about can be in a range or variety of different fuel forms, spent fuel forms.
Okay, let's go to FC 1.2 now. What is the level of theory desired for modeling of solvent extraction?
So I don't quite understand the nature of that question. So if you want to contact me offline, that would be great with more information. Thank you.
Okay, FC 1.2 again. Do all of the aspects in bullet point number 4 on your slide have to be addressed, or is it okay to just address some of the items, such as the radiolysis of an extractant?
Right. So it's not necessary, to address all of those areas. That's a non-exhaustive list. It was just intended to give you an idea of some of the areas that are of interest to us for separation. So you don't have to do radiolysis and computational modeling, and coordination chemistry. It's just those are some of the areas that you can look at.
Okay, FC 1.2. Is a mix of experiments and simulation desired, or is simulation alone acceptable?
Both are acceptable. Yeah, I like both ideas.
Okay, 1.2 again. For recovery of valuable elements and presumably isotopes, what level of purity is expected, such as a level available to commercial market or to a limited nuclear market?
Yeah, so that's a good question. Again, similar to the question in FC 1.1, we're not restricting that because, as you pointed out, there are a lot of different markets out there, right, that will have different requirements for the purity of the uranium or rare earths or whatever element that you're proposing to develop a separations method for. So we're not restricting you to that, but be sure to, when you're writing your proposal, tie it to some kind of application. But just in short, we're not dictating a specific purity for this because of the fact that there are a lot of different markets out there, both commercial and non-commercial, that could benefit from these separated elements.
Okay, FC 1.2. Is an ion exchange approach responsive to this call?
Yes, it is. And also, if you can develop a method for HALEU for FC 1.1, it also applies there.
Okay. Would liquid extractions with polymers also be of interest for 1.2?
Yep.
Okay, let's move to questions for FC 1.3. Would only ab initio MD-based simulations be considered? What about classical MD and development of potentials for molten salts that can be used to study large-scale and longer time-scale behaviors?
Yeah, so we're not restricting this to ab initio methods. You can also do, the classical MD methods as well. And yes, it would be interesting to look at them at longer time scales. That's totally fine. Yeah.
Okay. For FC 1.3, could the computational work include limited experiments for validations?
Yes, it can, but just make sure that, since that FC 1.3 is more focused on computational, and you probably want to, lean more towards that. But yeah, the idea of using experimental methods or experimental data, to collecting experimental data to support or to develop those computational models, that's fine. Yeah.
Okay, so for both FC 1.3 and 1.4, can modeling and experiments be included?
Yeah, that's certainly allowed. But again, like I said, for FC 1.3, it's more computational focused, and then FC 1.4 is more experimentally focused. But yes, you can have that combination. Nothing restricting you from doing that.
Okay, FC-1.3. What types of molten salt chemistries and thermophysical properties are of main interest? Salts for FHRs and MSRs and separations?
Yeah, so molten salts for all the different, so you're right, like FHRs, for MSRs, pyroprocessing. Those are all, any molten salts that are applicable for those uses are totally fine, yeah. Did I get all that question? I don't think I think there was a second part. Can't remember.
Let's see. Salts for FHRs and MSRs and separations? Are they okay?
Yeah, that's the pyro part. Yeah, they're all okay. I just wanted to make sure. I thought I heard something more
Okay.
than that. But yes, that's the pyro part. Yeah, that's applicable too. Mm-hmm.
Can a national lab postdoc be part of a full proposal with a university partner in FC 1.3?
Yes, they can.
Okay. Let's see. Here's a question about a proposal someone submitted. It says, one of our proposals based on only modeling with experimental support was rejected with a comment that the experimental side was not strong. Would you have any suggestions on how to improve a proposal that got a comment like that?
Well, I didn't see the proposal, so I don't know what kind of feedback to provide. But I think that as part of the NEUP application review process, if it's rejected, there's I think you get feedback in that case, right? But outside of that, I don't know because I don't have the specifics for the application or for your proposal. Sorry.
Okay, in FC 1.3 and 1.4, should the molten salt chemistry be targeted toward more reprocessing than molten salt reactors?
This one is inclusive. Like I said, it's both. I will say that, molten salt reactors, that's a big area of interest right now, but the proposals can apply to either one. They can focus on either area, the separations, or sorry, the reprocessing, or the strictly molten salt reactors.
Okay, now we're going to move to questions on FC 1.4. Mm-hmm. Are characterization methods such as X-ray and neutron scattering carried out at DOE national labs of interest for this work scope?
Yep, they are.
And for FC 1.4, is it desired to add some modeling to the experiments?
It's not required, but you can certainly do that, using the combination of the two. There's nothing wrong with that.
Would there be interest in conducting in situ synchrotron studies for FC 1.4?
Yes, there would be.
Okay, these are a little bit more general questions. So why are some work scopes for 2 years and others are for 3 years?
Oh yeah, I may not have explained that well in my presentation. So 3 of them are, I think, at 200K, and sorry, they're 2 years and 400K, and then one is for 3 years at 600K. So the first 2 are new work scopes. So they're just focused on developing innovative processes. And so as such, we decided that having a 2-year time frame was enough time to evaluate whether these innovative ideas are successful or not. The one for FC-1.3 is a computation-based one, which we found in general cost is actually less expensive than an experimental based project. And so that also explains why FC-1.3, which is a pretty well-established work scope. We've seen it, I think you've seen it over the last year or two being proposed. It's actually a longer 3-year project at 600K.
Okay, looks like our last question, and this is about having PhD students work on projects, and it says, You mentioned that the NAUP program wants to cultivate and grow the next generation of young scientists in this important area. However, the grants are only for 2 years. How does a 2-year university grant reconcile with a PhD graduate student that has 3 or 4 years of study? Do you have any thoughts on that, Christina?
Yeah, that's a good question. And I do want to say that even though these projects are for 2 or 3 years, it doesn't mean that, after 2 years you're done. Like that's it. There are ways in which, if the project is successful, because again, remember, some of those 2-year projects are more exploratory. We're focused on, trying out new innovative approaches. Even though those are only 2 years, there's still ways to extend those projects if they're successful. So something that starts out, in a new area can end up being, a graduate student's dissertation even. I would think, if it's successful. So yeah, these are more, again, focused on innovative methods. This is your chance to think outside of the box and come up with something new and exciting for not just your lab, but also for the nuclear industry at large.
So there was one question back in FC 1.1, 1.2, and part of it was very similar to previous one, but it also asked, does the goal of FC 1.1 and 1.2 also include separating highly radioactive actinides from the waste for further remediation?
Oh yeah, that's okay. That sounds similar to another question. I think the question is asking whether or not we're only restricted to recovering, uranium, plutonium, and other. Well, I guess uranium, plutonium, or are we also considering a recovery of other elements for remediation purposes? I think that's the question. Is that right?
That was the other one.
Yeah. So it is of interest, recovering isotopes for waste management purposes, for remediation purposes. But I think, again, because we want to come up with ways of recovering HALEU and plutonium, which I think are much more valuable, economical, like they could actually help improve the economics of reprocessing. That's more the focus. But don't get me wrong, I do see the merits of doing these recoveries for waste management, remediation purposes, right? But I think, again, for this one, it's really focused on getting those high value metals from the used fuel.
Okay, Christina, that looks like that's all the questions we have today. So I want to thank you very much for joining us today, everyone. And thank you, Christina, for presenting these topics to us.
Yeah, thanks. And you all feel free to email me at the email address listed here if you have further questions. And thanks a lot.
Thanks. Bye.